is a choice of emerging technologies which are adequate for use in an active control loop. There are electroactive materials, shape memory alloys, shape memory materials, magnetic strained materials, the MEMS system, plasma actuators, and some combustion actuators. And I go through them now and just explain what's behind these words and technologies. First of all, we've got the electroactive materials. Just found this nice animation here to show the principle. So you apply a strain onto the material, and this gives you a voltage output. And you can do the inverse job. You can apply a voltage and transform the geometry of the material. So there are two main families to do that. There's piezoelectric ceramics, piezoelectric materials, and there's electroactive polymers. The principle is simple. As you can see it here, it's highly efficient because it has a minimum current and a very high voltage. The last point, it applies to all these technologies. It still requires some considerable development. Principles have been shown that the step from the very emerging technology onto the product, that's a large step to take. Okay, let's go first into the piezo electric ceramics, piezo elements. They are often established by material lead, saccharide, titanite, but which has a very low temperature limit of 150 degrees Celsius. So a better choice is to take lithium niobate, which has temperature capability up to 800 degrees centigrade. But all these have very small displacement while producing high strain, high forces. So you will need a mechanical amplifier. And these amplifiers can be just simple levers or electrical structures inside of the gas turbine. And of course, all this has to be coupled with a temperature limit, the development to push the temperature limit. Here's an example of a piezoelectric actuator. So basically that's a stack of elements shown here, and this stack is needed to give you enough deformation. So you apply the current and you can see that the material will deform, as shown here. This rod here, this tube, would elongate. There are several forms of piezos, like sheets and tubes, all these kind of designs, and they are commercially available now. Now, electroactive polymers, that's a fairly new technology. It's not yet used in aerospace, but more for robotics. For example, moving robot faces are made of these electroactive materials. And the thing is that they have got very high strains, so large deformation at very low stress. So that's like an artificial muscle. It produces very high deformation by only applying small tension, small voltage. A possible application would be for morphing wings or morphing airfoils. Very high energy density, but of course temperature capability is limited. And as I said, no gas turbine specific developments have been found here. Oops. Now shape memory alloys are very interesting. The mechanism of shape memory alloys is that they've got two states of material properties. The first one is an austenite representation of the material, which can be transformed by heating, or by cooling in this case, to a martensite. So you can change the state by modifying the temperature between martensite and austenite, and this gives you a deformation, and that's like a memory effect. That's why they call shape memory alloys. They've got two states of material which can be activated or deactivated by temperature. And this temperature can be produced by current. They've got different principles for actuation. You've got a one-way memory, so just on and off state. You've got a two-way position, so bistable. You've got these two shapes you use in the actuator. Then you can have continuous movement as well. So you're in between.
So you would form the shape up at the right-hand corner. That would be the shape you would form under originally, and then you would actuate it to get the other shape, or vice versa, or both.
Depends on the temperature level. So when you're at low temperature, you're here. So temperature is on this axis.
You can use both stable states. Say all these goggles here have a low temperature stable state, but you can use both states dependent on the design. And you can use the thing in between, but accurate control would be a nightmare.
Yeah. So when you heat it, the material changes from here to here. And when you cool it, it changes from here to here. So often it's actuated just by heating. It's the typical application. But you could also think of the inverse effect.
What we have seen yesterday on the serrated chevron nozzles, they do heating for moving it inward into the flow, and the stable cold part is then that is withdrawn from the flow. It will remain there without being heated, but to put it into the other state, you have to heat it and maintain the heat. And when the heat goes away, it returns to its original shape.
But the second shape would have to be trained somehow. You have
Yes,
to form it.
yes, you have to train.
Good. Here's something about the characteristics of the shape memory alloys, advantages and disadvantages. So a very good thing is that the shape memory alloys produces high power, or has got a high power to weight ratio, which means that the output is large by only putting low energy into it. You can see here, it's on this chart, you've got weight or power to weight ratio over weight, and shape memory alloys, shape memory metals are here in this region. While normal DC motors have got a very low power to weight ratio, and hydraulic actuators have got an equal power to weight ratio, but the weigh very much. They are very large. So that's another point. You can produce shape memory alloys, shape memory devices which are very small and which weigh only very little. Designs are simple. Maybe you can recall the picture from yesterday with the nozzle. So it's a simple structure compared to a massive mechanic system. You can apply electric heating or cooling. You can have both directions. The disadvantage is that it's slow. The transformation is slow. It takes place within seconds and just got low strain. elongation. It's an actuator which is also called muscle wire, because there's a amount of wire going through that with a shape memory material, and therefore by just applying a voltage here, current, can move, for example, this lever. And again, that's commercially available. Good thing. So now, another technology is the magnetic strained materials. They've got a fairly easy principle. You apply a current with a solenoid going through that here, and you get an elongation of the material, so a deformation of this magnetostrictive material. These magnetostrictive materials are, for example, nickel alloys, but very interesting material is this terphenol D, which is commercially available. I think we had this discussion yesterday already. The interesting thing is that you can simultaneously sense and actuate, because there's a relation between the deformation and the voltage. So you've got both ways which you could use. So they are redesigned for smart actuators. They are very robust, and there's both these things, large and small devices. And here's an example of an actuator which has been fabricated with a magnetostrictive material. It's got a high force, only low stroke. So also low voltage. But good news is very high frequency. Okay. And this actuator, you can see here the coil moving around that part and just pushing here in this direction. Another technology is the magnetic shape memory alloys. So that's something in between shape memory and magnetostrictive. You can transform the material by applying a magnetic field to activate the material. Here's the principle of a sensor. So again, a solenoid activating a magnetic field and elongating this active material. Also, the nice thing is that that's commercially available, and there's a supply in Finland.